Okay, so we have compute engine in the background that says TPU BERT, so something interesting is going on. So welcome to a very special episode. This is an advanced episode, so I won't be explaining a lot of things. Um, I think I do explain a lot in my other videos, but in this one I'll be explaining very less. So be focused. Also, the code won't be released for 7 days since after the release of this video. So it's because when I release the code, people are just going to mostly copy paste it. But I want people to um, try it. So watch the video, do it yourself. Then, if you're not able to figure something out, ask me. I'll help you out in the comment section, and then I'm going to release a code after 7 days. And I would also appreciate that nobody else releases code before I do. Um, so let's get started. Yeah, so this video is about training BERT model, um, fine tuning BERT model actually, for a classification task, and we are going to use PyTorch and TPUs. So the first step is to set up a machine. So I was lucky enough to get some TPU nodes from Google. So I can just go to TPUs on my Cloud Console, and I can create a TPU node. Now you have to be very careful that you create a node where you have uh, it for free. So for me, it's free for some time because the hourly rate you see, like, it's quite high, and you have to choose TPU software version. So we can choose 2.1 when we are using TensorFlow 2.1 in one of the upcoming videos probably. But right now I'm going to choose PyTorch nightly, and you create the node. When you create the node, so I've already created the node, I don't need to create it again. It's gonna appear here. So I'm just going to start one of my old nodes, and then you need an instance. So you can create an instance in the same zone. That's very important. So my zone was Europe West 4A, and okay, we need 16 cores, 60 GB memory. And now, very important step is you change the boot disk. So scroll down to the bottom, and there is GNU Linux, but with PyTorch XLA, and you choose this one. I would rather choose SSD because this is much faster when you have data stored on the disk, and then you can just start it. You can create the image. So it's going to create an image for you. Again, I have already created an instance. I don't need to do it again. So this is my instance. It's here, and I can now SSH into it. But before that, we need to write some code. So what I'm going to do is I'm going to use data from an ongoing Kaggle competition. It's called the Google Quest question and answer labeling. So without going into much detail, so I will tell you what the data consists of. So it consists of a question title, question body, and answer. So these are our three main training columns: question title, question body, and answer. And you have 30 different labels. So it's a kind of a regression problem, I would say. You have 30 different labels. So if you want to know more about the dataset, you can take a look here, but that's not my priority in this video. My priority is to show how to run BERT fine-tuning on TPUs. So here we are in the terminal, and in my code server, and now we have to start writing some code for training. So let's see. First of all, where I start from is, first I create the model. So we can create a model. So BERT base uncased. Let's say that's our model, and it's going to inherit from nn.module. So now we need to import it. Okay, so we have that, and now you need to say, okay, the init function, what should we have here? Okay, so I got distracted. BERT path, the path to BERT model files, the config file, vocab file, and the model itself. And then you have to say superclass of BERT base uncased, the same class name, self dot underscore k, and self dot BERT path, I would say, is my BERT path, and my BERT model itself comes from transformers, so I have to import transformers. BERT model from pre-trained, and your path will be self.BERT path, and that's it. And I would also define a dropout, BERT drop. This is my dropout with 0.3, 30% probability, and an output function, output layer, which is a linear layer, and it has 768 input. Why? I will tell you now. And 30 outputs. Now I'll write the forward function. Self, what do we need? For BERT, you need IDs. So let's say we just need IDs, mask, and token type IDs. You need these three. So now BERT has a sequential output and a pooled output. So we are not going to use sequential output. We're just going to use pooled outs. I'm just going O2. So O1 and O2. O1 I have represented by underscore because I don't need it. And self.BERT IDs, attention mask is my mask, and token type IDs is my token type IDs. Now I don't generally write code this way, so you have everything in one file. So I like to split it up, but for this video everything goes in one file. And BERT out is self.BERT drop. Add the dropout to make it more generalizable, and final you have, or I can just say return self.out bo, and our model is done. So the pool output has 768 features, and that's why we have 768 as input here. And now the second thing is that you want to do is create the data loader. So I will say, okay, BERT dataset for training. It's my class. And now I would do an init function, init self, and what would this function to take? So we are going to use 3 columns: question title, question body, and answer. So for now, only these 3. Okay, and now self dot title equal to q title. Let's say okay, q title self dot q body. There's a question body, q body, and self dot answer equal to answer. We have that, and we need to define a len function that gives you the length of this dataset, which is same as return length of self dot answer or title or body, anything you want. Then you have to define a get item function that takes an index and returns you one input data. So you have question title equal to, I'm just going to say convert it to string if it's not already string. It should be string, by the way. Self.q title item. All of these are arrays or less. I mean q title, q body. So question title, we got it. Question body is str self dot q body and item, and answer equal to self dot answer item, and we also convert this to string. Okay, so we got all these 3, and now we need to tokenize it. So we need a tokenizer input. And we also need to know the max len. Okay, so self.tokenizer equal to tokenizer, and self.max len is my max len. So what I'm going to do is I'm going to create something like this. You have the CLS token, then you have the question title and question body, and you have sep token that separates the second string, answer, another sep to end it. So I don't know if I remember the correct order, but probably this is it. So I'm joining question title and body together, and another input string is the answer string. So I'd say inputs is my self dot tokenizer. Now a very cool thing with this tokenizer from Hugging Face is it has a encode plus function. So what it does is it takes strings. So in this case it takes question title plus question body, and my second input is answer. No, and I want to add special tokens. And max len is self.maxlen. So it's going to do its job and create me the string as I said earlier. So my IDs is inputs, input IDs, and token type IDs is inputs, token type IDs, and mask, attention mask is inputs, attention mask. So now we have the IDs, we have the token type IDs, we have the mask. Now what we have to do is we have to pad it. So padding length is self.maxLength minus the length of IDs, let's say, or token type or mask. All of them are going to have the same length. So your IDs become IDs plus 0 into multiplied by the padding length. And similarly, you have to do the same for token type IDs. So padding in the end and mask. So now we got all these things here. The next thing from here that we have to do is return, and we have to return some things. So IDs, so call it like torch.tensor. So now I have to import torch, and one more thing that I would like to add here is targets. Self.targets equal to targets. So targets is a numpy array, so its size is number of samples multiplied by times 30, sorry, because there are 30 targets. Torch.tensor IDs, and its dtype would be torch.long. So you got this one. Similarly, you have for mask, and you have token type IDs. So since I'm lazy, and then you have targets, which is torch.tensor self.targets item, comma, all columns, and d type is torch.float. Okay, so now we are done with two main components. One is the dataset and one is the model. So now we have to write two more components, and that's your training loop and evaluation loop. So I'm going to also define a loss function here. You don't need to do that. You can also do it inside your training. So, but if you want custom loss function, then it's better to just define once and reuse it. Return. So I'm not doing anything interesting here. Output and targets. So this is incorrect. It should be like this. That's it. So now we have got one more component here, and now we will start with the training loop. So what do we have in training loop? We have train loop fn. Let's say this is the training loop function, and this will take a data loader object, some model optimizer. It will take a device, let's say, and scheduler. It can take a scheduler, cannot take a scheduler, it's okay. And we have to first put the model in train mode, and we can do for batch index comma d in enumerate data loader. So you have the IDs is d IDs, mask is d mask, and token type IDs it should be d token type IDs. Okay, so you have it now. Now what you want to do is you need to transfer them to torch device. You also need targets, obviously. Targets is d targets, and IDs go to IDs.to device and same d type. Okay, IDs, mask, token type IDs, and targets. Okay, so we got these two. Fine. Now we zero grad the optimizer, and we pass everything to the models. Outputs is model ID is equal to IDs, mask equal to mask, and I'm writing and token type IDs is token type IDs. So you got them all, and your loss is loss function output comma target. So everything is in its place. Now you need to do the backpropagation step, backward, and optimizer. And if scheduler is not none, then you also do scheduler dot step. So I do this because sometimes you want to use a different scheduler, so that does the step after the epoch, so you don't need it here. So you have the train loop done. So eval loop function now. It will also take the data loader. It will take a model, an optimizer, and it will take a device. Okay. So now most of the stuff I'm going to do copy from here to here. Put model in eval mode. There is do we have targets? Yeah, we do have targets because we're going to just use it for eval, so everything remains the same. No optimizer step, no this gone. So if you look at the data over this competition, I mean there are 30 targets, right? So what I'm going to do is I'm going to keep them in a list, fin targets empty list, and fin outputs is an empty list. And here I'm going to do fin targets dot append. Now you have targets dot CPU dot detach dot numpy. So I just change it to numpy, put it on CPU, and now you do the same for fin outputs. This will be outputs dot up the CPU. So the thing is, we chose the last layer as the linear layer, So we need to apply a sigmoid function to it. So our targets are between 0 and 1, and we're calculating Spearman. So even if you don't apply a sigmoid, it's actually okay, because Spearman is your ranking. It depends on the ranking. So let's not do that. Let's not apply a sigmoid. And then we return np.vstack. So converting the fin targets, or let's say first we return the fin outputs, and then np.vstack fin targets. So we got them both. So we got the eval function, we got the train function. Now we need to train the model. So I say, okay, this is my run function that just runs the model, and I need to define a few things here. So I define the max len, train batch size equal to 4, let's say, epochs equal to 20, and now I need to read the dataset. So my dataset will be pd.readcsv input/train.csv, and there are some NA values, so I'm just gonna do this fill NA none. Need to import pandas now, and we also use numpy, so I'm going to import numpy. So we got everything, and now you have so now what I'm going to do is I'm going to split it, df train df underscore valid equal to model selection. Let's also import that from scale learn, import model selection dot train test split. So we have everything. So scalar model selection, train test split, dfx, comma, random state. Let's specify some random state 42, and test size 0.1. 10% of the samples are in test. So we have that, and now since we do indexing by index, I'm going to reset the index, df underscore train dot reset index, and drop the old index, and do the same for valid. So we got that. Now read the sample submission file, pd.readcsv, sample submission.csv, and my target columns are a list, sample.drop. If I just drop the ID column, QAID, comma, access equal to 1, then I'm left with all the target columns, and I can say train targets equal to df underscore train target columns dot values, so making it numpy array, and same for valid, so df valid, and this will be valid targets. Okay, so now we are almost there. We need to define the data loader, and we also need to define a tokenizer. So tokenizer is transformers dot BERT tokenizer dot from pre-trained, and the path to the tokenizer is my /input BERT base uncased. So there I've stored everything, and train data set now is BERT dataset training. And what does it take? QTitle will be dftrain dot question title dot values q body will be question body dot values, and answer is going to be train dot answer dot values. So I already know that these column names, yeah, you can check the dataset. And targets is train underscore targets, and then you have tokenizer, which is tokenizer that we have created, and max length. What did we call it? Max len. Okay, then max len is max underscore len. Okay, so was it correct, everything here? Max len and self dot max len. Okay, yeah, it looks fine. So we got the train data set, and then we want the train data loader. So this will be torch dot utils dot data loader, and this is taking train dataset, and batch size, train batch size, and what else? Shuffle. Yeah, okay, let's leave it there. And we need to do the same for validation. So let's see how I do it. So I did it wrong. Training, and it is still wrong. Okay, now it should be correct, and we don't have valid batch size. I'm just going to specify 4. So even if I do shuffle true or false, it doesn't matter. Let's make it false. And now we are ready to train. So first of all, we need a device. Now when we were training this on GPU, device was CUDA. So I mean, let's keep it that way. And if you need the model, so model is BERT base uncased, and it requires the BERT path. So path is BERT base uncased to device, and then you need a bunch of other things like which parameters you want to tune, which one you don't want to tune. So we don't have to decay on bias and layer norm, but I'm going to leave it here. And you need an optimizer. So optimizer will be let's say I chose Atom W, and this is also available in Hugging Face. So we need to import that from transformers, import W, and we also import a scheduler. So we now have almost everything, and we are ready to go. So I'm just going to say I'm just going to use all the parameters, and learning rate is equals to learning rate. I have to define the learning rate, so 3e minus 5, and should have the scheduler, which is get schedule with warm up. Okay, now close this, and this takes in optimizer number of warm-up steps, which is 0, and number of training steps. So it's number train steps. Now we have to say what's the number of training steps here. So train steps is int of len of train dataset divided by train batch size, and divided by, if you have accumulation, otherwise you can just then multiply by epochs. That's your total number of training steps. And now we can write the loop for epoch in range epochs. You can do train loop function that takes train data loader, model, optimizer, and device, and scheduler, and then we can have the targets. What did we have? Outputs and targets in the eval. So outputs and targets, and you have the eval loop function that takes the valid data loader, model, and device. And just for the sake of this competition, we can also calculate spearman. So spearman, let's say it's a list and it's a mean spearman. So what I'm going to do is for JJ in range t.shape1, p1 is a list, t, all rows JJ, and same for output p2. Your spearman coefficient will be, we calculate it from scipstats, spearman r p1 comma p2. And what I'm going to do is I'm just going to add np.nan to num, because in some cases when it's not defined, we don't want nan values in here, it's going to make everything nan. And spear.append coefficient, so we got that, and then my spearman will be just mean of all spearman that we have collected. And we can say, okay, print spearman equal to spearman. You can also print epoch. And we are done. So if name run. Okay, so now this is what we do when we train on CUDA. And to train on XLA devices like TPU, it's not so difficult. So what I'm going to do here is I'm going to import Torch XLA. So from import Torch XLA dot core dot XLA model as XM. So when you use Torch XLA, you have to remember you cannot do model.save, or sorry, torch.save model statics. So instead of that, you have to do xm.save, then model.stateDict, and model name model.bin. So it's going to convert to CPU GPU compatible. Otherwise you will have a lot of problems. I faced a lot of problems in recent days because of that. And you need to change the device. So device is xm.xla device, and learning rate and everything looks fine. We can now train it. Oh no, there's one more thing, and that's also very, very important. The optimizer.step changes to xm.optimizer step, and inside that you have optimizer, and that's it. That should be good enough to train on a TPU, but it will train only on one core. So first let's see if it trains at all. So now inside the terminal that we have, we can just activate the Torch XLA nightly conda environment. So we activate that. So you can also update it. So we'll take a look at Torch XLA repository, and you can update this nightly. So I updated it, and so I have to import a path, but you don't have to do it, you don't update. And then I'm going to go to I think I already created it, so let me create the file here. So what I'm doing is I'm just copy pasting it and save, and now I need to run it. So on Torch, on GPU, so sorry, TPU. So what you do is when you run it on TPU, you have to specify the TPU worker. So if you see the TPU nodes that you have this IP address. Port is always going to be 8470, and then you do python train.py. So you can also export as an environment variable xrt TPU config, or I like to just keep it here if I have multiple TPU nodes running, and then it should work. Let's see if it works. So we have an error, and I know the error, so let's try to fix it. So I'll just fix it here instead of going back to the code base. So, and the error was this should be max length, and then we try again. So I hope it's training, but it's not showing me anything, so I'm just going to stop it. Seems to be stuck. So let me see what happens. So in the code base, I'm going to add a few things so I know what's actually going on. And I'm going to say if bi %10 0 print loss. Sorry, yeah, 10 is okay. And loss, and bi equal to bi comma loss. So the batch index. So we have that now. The code itself looks fine to me. No, it doesn't. The code doesn't look fine to me. So we're missing something. What we're missing here is if you use only one node TPU core, you have to add barrier equal to true to the XM optimizer. So we got everything, and now we can go back to our terminal, which I think I've closed. Going back to our terminal, let's try to run the updated code, see if it's working. I hope it works now. We'll just see. Yeah, okay, so it seems to be working. So yeah, it's training on TPU, it's training on one core, it's training quite fast actually, not bad. So it's much better than training on CPU, but you know what's much better? To train it on multiple cores at once. So let's take a look at that. So to do the multiprocessing part, it's also very quite easy, and converting this code won't take much time. So first of all, I forgot something. So from scipy import stats, and I know that in this code it's going to give you some warnings because some values are going to be all zeros when predicted. So I'm going to do import warnings, and warnings dot filter warnings ignore. So all warnings will be ignored. So now we go back to our run function. So the first thing that we change is we add another argument called index in it. Now you will notice that index is not being used. So how multiprocessing works is it's distributing the data on different cores and then updating the model parameters. So your effective batch size will become your original batch size multiplied by the number of cores you have. For TPUs, it's 8. So we need to sample the data to every core. So I write train sampler, and my train sampler will be distributed data sampler from torch utils, torch data utils. So it goes something like this. So torch.utils.data.distributed sampler. Not very difficult. And inside here you have train dataset. So let's just write train dataset, and then you have num replicas. So the number of replicas. So you can get the number of replicas using XRT world size. So this is the number of cores, or if you have pods, then yeah, total number of cores that you have. And rank, you can also get this from get ordinal function, and you can also include shuffle equal to true here. Now in train dataset loader, you have to replace shuffle with sampler. So I've already done that. So it was like this, and now you change it to sampler. and you have to create a validation sampler. So I'm just going to copy this part here, put it here, change the name, valid sampler, valid dataset. Oh, sorry, it should not come here. It should come after the dataset. Okay, so valid sampler, valid dataset, and here you have sampler, valid sampler. Now for us, it doesn't matter if we do shuffle or not. I'm just going to remove it. The next thing that you have to do is adjust the learning rate. So now your learning rate will become the original learning rate multiplied by the world size, which is 8. And similarly, you have to divide here for the number of training steps. So we are done with this, and did we forget something? Yeah, so we forgot to import. Oh no, we have it. So import .xla.core.xla model as XM. We have that, and we will also import 2 more new things from. So import torch xla dot distributed dot xla multi processing as XMP, and import torch xla dot distributed dot parallel loader as PL. Okay, so we need these 2 more things. So now we have to change one more small thing. So let's see, we were here, we changed the number of steps. Now we need to change the data loader in training and evaluation functions. So our training and evaluation functions are here, and we say parallel loader is pl dot parallel loader, and that takes your argument, your train data loader, and current device in a list. So you got this one, and similarly you do it here for valid data loader. And now you have to change this. So this becomes paraloader dot per device loader current device, and the same thing will happen here. So you got everything in place. Now you cannot run it like this, so you have to change it, and it should become XLA multiprocessing dot spawn. So you have to spawn the workers, run, and procs equal to 8, which is the number of cores that we have. So that's also done. Now one more thing which is quite important is you need to change barrier true, remove it. So we are done with that too. And now we can see if this code is working for us in the terminal that we have. So here is the terminal. I'm going to remove train.py, and then I create a new file, same name, Lazy me. Hopefully everything is okay. We don't know until we run it. So let's run it. So same command and enter. Let's see what happens now. Okay, now it prints more stuff. So that's a good sign. It's printing everything for different workers. 8 different workers that we have. And let's see what happens now. Just to check what our batch size was. Okay, we can check it later. But now you can see like it's printing from each and every worker, and that's something we don't want to do. So what we want to do is we have to change a few things. So like the print functions. So what we do is xm.masterPrint. So it's going to print only on one. And we had one more print here, xm.masterPrint. And we used a batch size of 4, and that's underutilization of TPUs. So I'm going to set it to 32. So effective batch size now is 32 times 8, which is 256. And see, still going on. Let's see the terminal. And yeah, it's still going on, so I'm going to stop it. rm train.py. Paste the new code. And for multiprocessing, I also got some chai. I also want to say, if you're not watching the channel Chai Time Data Science with Sanyam Bhutani, it's quite good. He's interviewing very nice people, legends of data science, legend data scientists. So take a look. And now we can run it. And hopefully it works. Let's see. So it seems to be working fine. So overall it's doing probably like 21 batch indices, and that means it's using all the TPUs. So you can see the first epoch Spearman quite low, 0.06. I hope it improves in the second one. It's taking around 1 minute, so this is one epoch. It's taking 1 minute for one epoch. And on my home computer, which is where I have two 2080 Ti's, it takes 5 minutes per epoch. And Spearman is increasing, everything is going well, it seems, so I'm happy, and you should be too. So going back to our code now, TPUs are very tricky. So since your batch size has increased quite a lot, your effective batch size is quite huge, you need to experiment with different batch sizes and different learning rates, different number of steps of training to make it work fine. And it has taken me quite a lot of time to make it work, but yeah, I hope this code will help you. So remember not to share it right now, because if you share it, people just copy paste. So let people try it on their own, and once you code it, you will be very comfortable transferring it to a different domain or using different models. It's quite easy. And finally, you can just go back and take a look at what's happening here. Okay, it has improved further. So it's going pretty well, it seems. So now I have not covered multi-threading. Yeah, one more thing with multiprocessing on TPUs, it's going to copy the train data loader on every device. So if you have a large data set that you're loading in memory, first of all, you should not do that. And if you're doing it, be prepared to get out of memory errors. Happened to me a lot of times. And in the end, when it saves the model, you can just load it as you load the PyTorch models. And I've also created a kernel, and I'm going to post the link in the description box. You can take a look, and that kernel is only the inference. It's going to give you a very low score, but you can improve it. Thank you very much, and thank you for watching the video. If you have comments, if you have done something wrong here, let me know, and I would be happy to incorporate your comments in my next videos. Thank you very much.